Imagine your primary data center suddenly loses all power. Like, the screens go black, the
Yeah.
servers just die.
Oh, complete nightmare scenario.
Right, a total nightmare. So are your critical virtual machines instantly migrated without interruption, or do you face catastrophic downtime?
Well, the answer to that exact question is what separates a novice from a true expert when you sit down for the 3V0-23.25 exam.
It really is. It's the ultimate test of understanding not just what a system does, but how it behaves when the absolute worst happens.
Exactly.
And that is exactly what we are tackling today. So welcome to the deep dive. If you're joining us, it's because you are preparing for the 3V0-23.25 exam.
And we have a massive stack of highly technical notes right here.
Oh yeah, we do. Entirely focused on mastering the key concepts and assessment criteria for this certification. Our mission today is to, well, basically shortcut the studying process for you by pulling out the absolute most critical nuggets of knowledge.
Yeah, we're going to give you a step-by-step, question-by-question analysis of 10 rigorous practice scenarios.
But before we get into the weeds, let's establish the ground rules of the 3V0-23.25 exam based on the source material, just so you know exactly what you are up against.
Right, so when you sit down in that chair, you will have 135 minutes to navigate 60 questions. You are aiming for a passing score of 300. The exam is administered in English, and it comes with a price tag of $250.
So the stakes are real, and the clock will absolutely be ticking. To give you an edge, I promise you right now, I will read every single practice question we cover and every single option, A, B, C, and D, in full.
Every single one.
Every single one. Then we are going to tear into the underlying problem-solving logic. Because passing isn't just knowing the right answer, right? It's knowing the exact mechanical reason why the other choices are dead wrong.
Yeah, you have to know the why.
Exactly. So let's start from the ground up, literally. Before you can scale a system, you have to understand the mandated building blocks of the architecture. And I'm looking at question 5 from our practice set, which tests this perfectly.
Let's hear it.
Okay, here we go. When validating the storage design for the management domain in a standard VMware Cloud Foundation architecture, which storage type is exclusively mandated for the principal storage component?
Okay, and the options.
The notes give us 4 options here. Option A suggests external block storage. Option B proposes VMware vSAN. Option C offers network file system. And finally, option D is virtual volumes.
Right, so the correct answer here is option B, VMware vSAN.
Okay, but I have to push back a little here for you. Why is it exclusively mandated? Like, why couldn't you use standard network file system, which is option C, or even external block storage like option A? Plenty of global data centers run perfectly fine on those.
Oh, they totally do. But we are specifically talking about the standard VMware Cloud Foundation, or VCF, architecture's management domain.
Right.
Think of the management domain as the brainstem of the entire data center. The source material explicitly states that vSAN is required because it ensures tight integration, automation, and consistent lifecycle management across the entire stack.
So it's about the automation engine.
Exactly. SDDC Manager needs to control the hardware directly. If you use external block storage, or NFS, you suddenly need third-party plugins, separate storage arrays, and manual intervention to update the storage firmware.
Which breaks the automation.
Yes, vMan is baked directly into the hypervisor kernel. It allows VCF to automatically update the storage alongside the compute, which is a core design principle of the platform. So options A, C, and D, external block, NFS, and virtual volumes, are incorrect because they simply cannot provide that native, unbroken chain of automated lifecycle management.
Okay, let's unpack this, because if vSAN is the mandated brainstem, we need to understand how it actually operates under the hood. Which brings up a massive architectural shift covered in question 1 regarding the vSAN Express Storage Architecture, or ESA.
This is a huge topic.
It really is. Let me read the exact wording of the question. In a VMware Cloud Foundation environment, utilizing the vSAN Express Storage Architecture, which underlying hardware capability is fundamentally required to leverage its performance enhancements compared to the original storage architecture.
And what do we have for options?
Here they are. Option A, single-tier, highly resilient, non-volatile memory express storage devices. Option B, dedicated cache drives using enterprise-grade solid-state drives. Option C, hardware-level storage controllers with battery-backed write cache. And option D, fiber channel host bus adapters for back-end storage networking.
Okay, to really understand this, we need to talk about why the original storage architecture even existed. Think of the old architecture like like a busy restaurant kitchen.
Okay, a restaurant kitchen.
Yeah, you had spinning hard drives or slow SSDs acting as the slow kitchen line, and you needed a fast waitstaff, basically a dedicated cache tier of really fast drives to run the orders back and forth to keep things moving.
Right, a two-tier system, cache and capacity, like an old hybrid car engine.
Exactly like that. But ESA changes the game entirely. ESA replaces the entire restaurant with a massive team of high-speed master chefs who don't need waitstaff at all. It just completely drops the dual system complexity. So the correct answer is option A, single-tier, highly resilient, non-volatile memory express storage devices.
Because it's all about that NVMe speed. The drives are so fast, they just don't need a buffer anymore.
Precisely. ESA is built specifically to take full advantage of modern high-performance NVMe storage, where every single drive can handle massive throughput instantly. And this tells us exactly why option B is explicitly incorrect.
Because ESA eliminates the need for separate cache tiers.
Right, so you don't use dedicated cache drives at all.
That makes perfect sense. And I guess that leaves C and D.
Yeah, and they are completely off the mark based on the actual mechanics. Option C talks about hardware-level controllers with battery-backed write cache. In a modern software-defined storage world, hardware controllers actually create bottlenecks.
Oh, really?
Yeah, vSAN wants direct pass-through access to the drives. And option D talks about fiber channel host bus adapters, which is back-end networking, not the fundamental single-tier NVMe design that gives ESA its power.
Okay, you mentioned NVMe speed there, which brings up a huge debate in virtualization right now, how that incredibly fast storage actually communicates over the network when things scale out. Here is question 7 from the notes that tackles this head-on.
Go for it.
When comparing network-based storage protocols for a high-performance database workload in a virtualization environment, what is a primary architectural advantage of utilizing non-volatile memory express over fabrics instead of traditional internet small computer systems interface?
The classic NVMe versus ISCSI debate.
Yep. Let's look at the options. Option A, it significantly reduces storage protocol overhead and latency. Option B, it inherently provides synchronous replication across global distances. Option C, it eliminates the need for any underlying physical network infrastructure. And option D, it relies exclusively on legacy host bus adapters for data transmission.
Okay.
Now, I know you might be thinking, isn't traditional ISCSI perfectly fine for virtualization? Like, we've used it forever.
We have. But what's fascinating here is how the demands of modern workloads expose the limits of older protocols. ISCSI was built on the SCSI command set, which was literally designed in the 1980s for tape drives and spinning disks.
The 1980s?
Yeah, it's ancient in tech years, and it requires a massive amount of translation. The CPU has to take a modern request, wrap it in a SCSI command, wrap that in a TCP/IP packet, send it, unwrap it, and translate it again. It's incredibly inefficient.
That sounds exhausting for the CPU.
It is. NVMe over Fabrics, on the other hand, skips almost all of that translation. It speaks the native language of the flash memory across the network.
So it's basically taking that ultra-fast NVMe connection we just talked about and stretching it across the data center with almost zero translation penalty.
Exactly.
Which makes option A the correct answer. It significantly reduces storage protocol overhead and latency.
Spot on. It uses a much more efficient command set and dramatically reduces CPU overhead. Now, let's dismantle the distractors. Option B is wrong, because NVMe over Fabrics optimizes how data is transmitted. It does not inherently provide synchronous replication across global distances.
Right, that's a different software layer entirely.
Exactly.
And option C says it eliminates the need for any underlying physical network infrastructure. I mean, that's just silly. It's literally called NVM over Fabrics. The fabric is the network. You still need switches and cables.
Completely correct. It's not magic Wi-Fi storage. And option D is incorrect because NVMe over Fabrics is a modern protocol designed to bypass legacy bottlenecks. It absolutely does not rely exclusively on legacy host bus adapters.
Okay, so now that our fundamental hardware and management domains are set, let's shift gears. How does an architect scale resources and manage policies without taking the whole system offline? This brings us to question 4.
Scaling is where things get really fun.
Oh, definitely. An enterprise needs to scale storage capacity for a specific workload domain independently of compute resources. Which VMware storage feature allows a vSphere cluster without local storage to consume storage resources from a remote vSAN cluster?
All right, what are the choices?
Option A, Storage Distributed Resource Scheduler. Option B, vSAN cross-cluster capacity sharing. Option C, Virtual Volumes Array integration. And option D, Local disk path multipathing.
You know, this sounds to me like Ordering takeout from a restaurant because your own kitchen is too small.
Ah,
Like you have the dining room to compute, but you need someone else's kitchen, the storage.
I love that analogy, and structurally, that's exactly what is happening here. You are decoupling the compute from the storage. Traditionally, vSAN required every cluster to have its own local disks.
Right.
But with modern VCF, you can have a cluster of servers that only have CPUs and memory, and they just mount the storage from a completely different vSAN cluster over the network.
Wow.
So the correct answer is option B, VSAN cross-cluster capacity sharing. Okay, so why are the other options structurally wrong then? What about option A, Storage Distributed Resource Scheduler, or SDRS?
SDRS is a mechanism that automatically moves existing virtual machines around between data stores to balance the load. It does not possess the capability to allow a diskless compute cluster to magically attach to a remote vSAN.
Got it.
And option C, Virtual Volumes Array Integration. That's an API set that deals with third-party external storage arrays like a Dell or NetApp SAN. It has nothing to do with sharing native vSAN capacity.
Makes sense. And option D?
Local disk path multipathing is about providing multiple cable routes to local disks for redundancy. Since our compute cluster has no local storage in this scenario, option D completely misses the premise of the question.
Brilliant breakdown. All right, moving to question 8, which introduces a concept we haven't touched on yet, but it's essential for how vSphere actually talks to these storage systems.
Let's hear it.
In a VMware Cloud Foundation environment, utilizing virtual volumes for a workload domain, what is the primary role of the storage awareness provider component? And the options are option A, to encrypt data in transit between the host and the storage array.
Okay.
Option B, to perform load balancing across multiple active storage paths. Option C, to establish out-of-band communication between the management layer and the storage array. And option D, to automatically back up virtual machine snapshots to a secondary site.
So the storage awareness provider, also known as the VC provider, is a critical control mechanism. You really have to understand the difference between the data plane and the control plane here.
Okay, what's the difference?
The data plane is where the actual zeros and ones of your virtual machine files are traveling. The control plane is simply the management conversation happening behind the scenes. Option C is correct, to establish out-of-band communication between the management layer and the storage array.
Oh, so out-of-band means it's not the path the actual data is traveling on. It's just vSphere whispering to the storage array, asking things like, hey, do you support encryption? Are you solid state or spinning disk? So you can use policy-based management.
Exactly. It's a separate control path that just provides storage capability information back to vSphere. And once you understand that it's purely a control plane mechanism, the distractors just fall apart.
Let me take a swing at eliminating them then. Because it's just a control and communication path, it never touches the payload data. Therefore, it's definitely not encrypting data in transit, so option A is out.
Right.
It's not moving actual I/O around to load balance across active paths, so option B is mechanically wrong. And it certainly isn't an automated backup tool moving huge snapshots to a secondary site, so option D is completely factually incorrect.
Spot on. It's purely about communication.
Nice. Well, here's where it gets really interesting. Speaking of policy management, question 3 tests exactly what happens mechanically when you change those policies on the fly.
Oh, this is a good one.
An architect updates an existing storage policy by changing the failure tolerance method from mirroring to erasure coding. When this updated policy is applied to existing virtual machines in a running vSAN cluster, what happens at the storage layer?
The option.
Option A, the system aloots the administrator that policy changes cannot be applied to running workloads. Option B, the virtual machines are temporarily suspended while the underlying storage is reconfigured. Option C, the system rebuilds the object components in the background to match the new space efficiency requirements. And option D, the new policy only applies to newly created data while existing data remains in a mirrored state.
Okay.
Now, if I'm an architect and I change the fundamental mathematical way my data is stored, I would assume there's going to be massive downtime. Like mirroring just takes a 100 gigabyte VM and drops a dumb 100 gigabyte copy on 2 different hosts. But erasure coding literally shreds that data into tiny blocks, calculates complex algebraic parity chunks, and scatters them across multiple servers. Doing that live seems insane.
It really does seem insane. It is a massive structural change, and the math behind it is incredibly heavy, but vSAN handles it elegantly. The correct answer is option C. The system rebuilds the object components in the background to match the new space efficiency requirements.
In the background, so running workloads just keep chugging along.
Exactly. vSAN applies the new policy to existing objects by calculating all that parity math and reorganizing the data components seamlessly without interrupting the virtual machine's I/O at all.
That is wild.
It is. That's why option A is incorrect. The system absolutely does not block you from applying changes to running workloads. Flexibility is the whole point of software-defined storage.
And I guess that completely rules out option B as well. The virtual machines are not temporarily suspended. There is zero downtime required for this massive mathematical operation.
Right. And option D is a very common trap for test takers, but it is entirely false. The new policy absolutely applies to the existing data, not just new data. The system immediately goes to work rebuilding what's already there to comply with the new rule.
Amazing. Okay, we've built the system and scaled it, but the true test of a VMware architect and a major focus of the 3V0-23.25 exam is how the environment reacts to failures, outages, and necessary maintenance.
The real-world stuff.
Exactly. Let's look at question 6. A storage architect is configuring a highly available vSAN cluster across 4 server racks to ensure that virtual machines remain accessible even if an entire rack loses network connectivity, which configuration must be properly defined.
Options.
Option A, enhanced vMotion compatibility guidelines. Option C, high availability admission control policies. Option C, storage distributed resource scheduler rules. And option D, custom vSAN fault domains.
The key phrase in the question is an entire rack loses network connectivity. You're talking about physical failure boundaries. So
Yeah.
option D is the correct answer. Custom vSAN fault domains.
Fault domains.
Yeah, without fault domains, vSAN might accidentally put all the mirrored copies of your data onto 3 servers that happen to live in the exact same physical rack. If the top of rack switch dies, you lose everything. Fault domains let you map the physical topology so vSAN knows to mathematically distribute data replicas across different physical racks.
Now, I look at option B, high availability admission control policies, and that sounds like a very real, very important VMware concept. Why is it mechanically wrong here?
It is a real concept. HA admission control ensures you have enough spare CPU and RAM capacity in the cluster to restart VMs if a host fails. But it has absolutely nothing to do with defining the physical storage placement of the actual data blocks.
I see.
Only fault domains dictate where the chunks are written. And options A and C EVC baselines for CPU compatibility and SDRS rules for balancing data stores are entirely unrelated to physical rack-level redundancy.
Got it. Now, question 9 deals with something that sounds simple, but is actually crucial for making all this background magic happen.
Let's do it.
During the operational lifecycle of a vSAN cluster, what is the critical purpose of maintaining sufficient unallocated slack space within the data store?
Slack base.
Yep. Option A, to serve as a dedicated repository for virtual machine templates. Option B, to provide necessary capacity for transient operations and internal component rebuilds. Option C, to guarantee sufficient storage for external third-party backup agents. And option D, to act as an isolated, secure enclave for compliance auditing logs. You know, I think of slack space like one of those sliding tile puzzles you played with as a kid.
Oh, that's a great way to look at it.
Right. To move the pieces around, calculate parity, and solve the picture, you absolutely need that one empty square. Without the empty square, the puzzle is frozen solid.
If we connect this to the bigger picture, that empty square is exactly what slack space is, mechanically speaking. Option B is correct. To provide necessary capacity for transient operations and internal component rebuilds.
Just like the puzzle.
Exactly. Think back to our discussion about changing from mirroring to erasure coding. To do that background math and shuffle all those shredded data chunks around across the host, vSAN needs free blocks to temporarily hold the data while it reorganizes.
And if you don't have it, those critical operations literally fail because there is nowhere to write the intermediate data. So it's not just wasted space.
No, it's essential operational overhead.
Yeah.
And this makes the mechanisms of the other options obviously wrong. Slack space is not a managed folder. So it is not a dedicated repository for VM templates, meaning option A is out.
Right.
It is not allocated to external software, eliminating option C for third-party backups. And it is certainly not a partitioned, isolated, secure enclave for compliance logs, so option D is incorrect. It's raw, unallocated capacity for internal system mechanics.
Makes total sense. Okay, next is question 10, bringing us back to the automated lifecycle management we touched on at the start with SDDC Manager.
Full circle.
Yeah. How does the SDDC Manager guarantee continuous storage availability when executing automated lifecycle management updates across a workload domain? Option A. It suspends all virtual machine operations until the storage layer is fully patched. Option B. It temporarily reduces the fault tolerance of all objects to 0 to speed up host reboots.
Yikes.
Yeah. Option C, it relies on synchronous external array replication to serve read requests from a remote site. And option D, it systematically evacuates workloads and storage components from individual hosts sequentially.
So SDDC Manager is the orchestration engine, and its primary mandate during updates is non-disruption. The correct answer is option D. It systematically evacuates workloads and storage components from individual hosts sequentially.
Sequentially.
Yes, it uses vMotion to seamlessly slide the running VMs to another host, patches the empty host, brings it back online, and then moves to the next one.
I have to ask, though, why not just use option A, like suspend all the VMs, patch the whole storage layer at once, and turn it back on? Wouldn't that be mathematically faster?
It might be faster for the administrator, sure, but it directly violates the core requirement of the question, which asks how it guarantees continuous storage availability. Suspending operations is, by definition, an outage. That rolling sequential approach prevents service disruption.
Good point. And what about B and C?
Option B is wildly incorrect. Reducing fault tolerance to 0 means if a single drive fails during the update, your data is permanently destroyed. SDDC Manager would never do that.
Right, that sounds terrifying.
And option C is wrong because SDDC Manager manages native vSAN, not external synchronous array replication to remote sites for a standard local patching process.
Okay, we have reached the final scenario, question 2, and this one pushes the environment to the absolute physical limit, fulfilling the promise of our hook at the beginning of the show.
The big one.
A retail company operates a VMware Cloud Foundation workload domain with a vSAN stretched cluster spanning 2 physical data centers and a third site hosting the Witness appliance. If the primary data center experiences a total power failure, what is the immediate expected behavior of the virtual machines previously running in the failed site?
Total failure.
Total failure. Option A, they remain offline until an administrator manually initiates a site failover process. Option B, they are transparently migrated without interruption to the secondary site. Option C, they enter a suspended state and wait for the primary site power to be restored. And option D, they are automatically restarted on the available hosts in the secondary site. Now, wait a second. I thought vSphere was practically magic. We always hear about vMotion and zero downtime. Why isn't the answer option B? Why aren't they transparently migrated without interruption?
Because the scenario specifies a total power failure. If the power suddenly cuts out in the middle of the day, the memory states of those running virtual machines is instantly wiped out. There's literally no time to copy active memory over the network. Live migration, or vMotion, requires both the source and destination servers to be powered on and communicating to synchronize the memory delta.
Ah, of course. If the plug is pulled, magic can't save the active RAM.
Exactly. So option B is a massive distractor designed to catch people who assume vSAN stretched clusters offer zero downtime failover for everything. They just don't for sudden hard failures. The correct answer is option D. They are automatically restarted on the available hosts in the secondary site.
Okay, so how does that actually work?
vSphere High Availability detects the loss of network heartbeats. It checks with the Witness appliance at the third site to confirm it's not just a split-brain network partition. And once it verifies the primary site is dead, it immediately issues boot commands to power on the VMs at the surviving site.
Which means there is a brief interruption while they reboot, but it's entirely automated. Which knocks out option A. You don't have to wait for an administrator to drive to the data center or log in manually to initiate failover.
Correct. And option C is mechanically impossible because they don't sit around suspended waiting for power to come back. You can't suspend a VM if the hardware it's running on has no electricity. HA takes action immediately to restart them from the surviving disk replicas and minimize downtime.
Well, good luck with your continued learning, and we hope this is giving you the edge you need for the 3V0-23.25 exam. Keep digging deep.